Hey, so great to be here. Like, I didn't know of this conference before until a good friend of mine, Tycho, who's here as well, actually made me aware of that. And I have to say, this is really good. Like, a lot of technical people around here, a lot of good questions in the talks. Like, I enjoy it a lot so far. So thanks for that, and thanks for having me. Yeah, so I'm Christian. I work as a software engineer, and I've been involved in the LexC and LexD project for some time now, even before doing this professional. Like, I have done some of that work even when I still was at university. So just a quick recap. I'm going to talk about system containers today, and so the LexC project, which is, I guess, the origins, or one of the origins of system containers. I mean, there have been a lot of projects before that predate that work, OpenVZ and so on. The Virtuoso guys have done work in this area as well. LexC was founded in 2008. I think it was founded still by Meiosis, and then it moved into IBM, and it was maintained mainly by Daniel Letzcano, and then at some point Serge Hallen and Stefan took over, and like it got a proper rewrite, and that's about 2013 when we released a stable API, and then since then we haven't broken API. I think we have done some major reworks in 2017 with LexC 2.1. And there's going to be another big rework coming in 3.0. So there's actually a lot of work that's been going into making system containers a thing. There's a lot of, I hope there's at least some knowledge that we have in this sort of area. And actually, I want to start by talking about Linux containers in general before like going on about why I think, or what the reasons are for why system containers are a little bit special in comparison to process containers. And one of the statements that I wrote up on here is containers don't exist. And that's it, like that's my talk. I'm now leaving. No, I'm just joking, but I mean, to some extent, thinking about containers in general and thinking about containers in the Linux kernel, I think has gotten a lot of people to the point where they are sort of convinced that containers don't actually exist. I mean, think about the mailing list thread on LKML that wasn't posted not a long time ago, where basically the discussion was, let's make containers an in-kernel thing. That's the easiest way to essentially put it. That's weird, but go away, ask questions right there. I don't know why this is there. So let's make containers an in-kernel thing. What does it mean? Well, it basically means you have some sort of function, right, that you call, I don't know, create container, and that gives you a handle back from inside the kernel, and then you have an object, which is a container, which you can do things with. That's sort of the idea. But I don't think this is actually worth it implementing it anymore. So I don't care about this approach in general. Like, I care about the implementation and the implication. And the implication here actually is that containers don't exist as kernel objects, right? I mean, and this is sort of different, and please yell at me if I'm wrong in this area, but this is different from what you, for example, get with FreeBSD jails or Solaris zones, right? I mean, they have an actual container concept, which is to some extent nice from a security perspective, I think, because you get a set of well-defined criteria that actually tell you what a container is. Sort of, it's a nice top-down kind of approach that you have to using containers. In contrast, actually, to this approach, the Linux kernel doesn't really tell you what a container is at all. The kernel sources, if you look at the kernel sources themselves, then you see they don't really tell you a lot about what containers actually are. Instead, what the kernel does, what the Linux kernel usually does, is just expose a bunch of interfaces to user space that allow you to limit resources or isolate processes or restrict access to certain kinds of information. But the interesting thing is that all of these interfaces were not necessarily designed with containers in mind. So that means the kernel doesn't give you any kind of guarantee about that. Like, for example, let's say you use namespaces and C groups, and let's assume that they don't work nicely together. The kernel doesn't give you any kind of guarantee that that these interfaces work nicely together. I mean, the reason is that most of these interfaces weren't designed with containers in mind. Mount namespaces being one example. I don't think mount namespaces, the original first mount namespace clone UNS, was designed with containers in mind. Another good example, I think, are C groups. And again, correct me if I'm wrong. C groups weren't designed with containers in mind. They just were a convenient way to basically limit system resources for a set of processes. A container is basically, in Linux, created by combining a bunch of those kernel interfaces. And don't worry, I'm not going to go into the details of actually how to combine them or what a container is. I think we're past 2008, and I guess most people in this room know what containers are, right? I mean, you sort of have a conception of what a container is? Yeah, okay, so that's pretty good. So you have a bunch of interfaces like namespaces, C groups, and pivot root, and LSM, and so on, and you can slam them together, and then you can make up your own kind of version of what a container is, I think. The thing is, as I said, the Linux kernel doesn't define what a container is, but actually I think this is pretty nice at this point. Because it means you can have a range of different types of containers. If you look at the landscape out there, are so many different container runtimes or container-like concepts. For example, there is Singularity, there is runC, there is Rocket, there is libLXC, there is systemd nspawn. There's a bunch of container runtimes. There are a bunch of different concepts of what a container actually is, and I think this is actually one of the strengths. It's a weakness and a strength at the same time of containers in Linux. So these interfaces can be combined in such a way that you can isolate a set of processes, right? We know that, or a set of processes or a single process. That depends on what kind of conception you have a container and what you actually care about. But here is one thing where I actually want to be opinionated about what a container is, and this is usually quite, I guess, to some extent controversial. But that's good, so that means you can yell at me later on, and we can have a discussion about this. I think I consider nothing a valid container for me. Remember, I'm coming from a system containers perspective that doesn't employ PID namespaces. Mainly because PID namespaces, basically it defines a completely new system. And this is true for any implementation basically that considers processes its smallest building block. So conceptually, the smallest building block of an operating system for me is a process or a thread, if you want to put it like this. And cloning a new PID namespace, creating a new PID namespace is like saying here, this is a new system, this is a new thing, this is a new entity. So I said I consider nothing a valid container if it doesn't employ PID namespaces. What I mean by this is I consider it, so to speak, a necessary condition for something to be a container, but it's not necessarily sufficient. Meaning, just because you have a PID namespace doesn't mean you're automatically running in a container. But another argument, apart from this argument I was making right now, I think my argument comes from the semantics of PID namespaces, actually. This is another question of mine. How many people are sort of familiar with PID namespaces and how they work? Okay, at least a few, so I'm not going to bore most of the room. So the thing is that PID namespaces, for one, are one of the few namespaces that are properly hierarchical. So that means they are nested into each other, which means each PID namespace to some extent forms a separate system. And this is true also for user namespaces, if I remember correct, but basically every other namespace is sort of flat. This has many reasons. One of the reasons is that it's more performant, actually, to implement them in a flat way than to actually nest them inside the kernel. But leaving aside this whole nesting argument, there is also the point to be made about cloning a new PID namespace, promoting the process that basically is spawned in there, the first process that is spawned inside of a PID namespace, to a very special kind of process, namely PID1. So as soon as you clone a PID namespace, you fork a new process in there to have it become a proper member of that PID namespace. You have you're now the init system, and this actually implies a lot, namely that any process that from now on gets spawned inside of that PID namespace, inside of that container, is ultimately under your control. So to go into this in a little more detail, so what, for example, happens if you kill PID1 inside of a PID namespace? What, from a kernel's perspective? a kernel actually sick kills all other processes that are running inside of that pit namespace. And also, what happens if, for example, the parent, like you clone a child inside of a pit namespace, and the parent dies. So the child gets reparented, right? To pit 1. But which pit 1? The pit 1 on the host or the pit 1 inside of the pit namespace? Actually, the pit 1 inside of the pit namespace. That's the proper reaper, so to speak, for this thing. So this becomes even more intricate when you now consider that that pit namespaces also enforce what I would like to call standard init behavior. So it means that, for example, processes that are proper member of that pit namespace, or if you set an S into a pit namespace from outside, and you now want to send signals to pit 1 inside of the container, then pit 1 will only react to signals, kind of trivial, for which it has established signal handlers. That's one thing. The second thing is that you cannot send sigkill or sigstop to pit 1 inside of the container while being a member of that pit namespace. So the kernel will simply not deliver this signal to the init system, which is kind of what you expect from init on the host, init from the host as well. So, but for processes outside of that pit namespace, for ancestor or parent pit namespaces actually, given the necessary privilege of course, you can always send sigkill and sigstop to pit 1 inside of the container, which means like the parent pit namespace or a parent pit namespace can always kill pit 1 inside of a container, or kill the whole container, barring any exceptional bugs. And by the way, I didn't say this before, but to come back to this nesting thing for pit namespaces I mentioned, it also means that the host pit namespace, so the first pit namespace that gets created when the init system boots, it sees all of the processes of all of the containers. I'm currently not aware of any way to hide the pits inside of a container from the parent pit namespace. So you always see everything that is running on the system at all times for anything that is a descendant pit namespace, so to speak. But what happens, for example, I said like the kernel sick kills everything when pit 1 inside of the container dies. But what, for example, happens? Yeah, what happens actually to a pit namespace when pit 1 inside of the pit namespace is not there anymore? And it's interesting, and sort of it's actually a situation that is pretty hard to sort of come by, but you can sort of mock this behavior by doing an unshare, which basically allows you to. Oh, this is going to be interesting. Which basically allows you to unshare parts of your namespace. So we unshare a user namespace first, so that we don't need root privileges, and then we do create a new pit namespace. And so what you see right now, the process that has created this original pit namespace actually is not around anymore. And so every time you try to spawn a new process in there, the kernel will react basically with enomem. So you, for example, ls, that would be executing a new process, right? ls, you try to do ps-ogs, if you try to do anything in there, you cannot. And it's basically because the kernel at this point, init has died, so basically the kernel is telling you, that's not functional, I don't know what you want from me, like there is no process in there that is doing any of the tasks I expect from a pit namespace, or that I expect to be handled in a pit namespace. So this is quite interesting insofar the kernel considers to be a necessary and sufficient condition for a pit namespace to be functional. But it's also interesting from this whole, I think, to me at least, is that this is much more in line, pit namespace semantics are much more in line with running a whole init system than it is actually just with running one single process in there. Of course, like we're at the point where sort of process containers are the thing we're all sort of talking about, and you can see like there's a massive landscape for process containers out there, and it's obviously an interesting concept. But for a long time, actually running process containers was, to me, to some extent done in a faulty way. And what I mean by that is usually like at the beginning of Docker, for example, when you ran a Docker container, you basically just got a single binary, a bash shell, right, or an Nginx or an Apache inside of a like container that also involves PID namespaces. But the thing is, none of these things is even remotely able to handle signals, read children, and so on. It's not really a good way to run a process containers, which is why, for example, libelixy since 2008, basically since this thing existed and Daniel Eltzkano started writing the original implementation. Started the original implementation, had what is called a stub init process or a mini init process. And I've seen recently, like Docker switched to this as well. I think they have Docker init by now, and systemd nspawn now also lets you specify, I think, a command line flag argument, --pid2, which basically means they run a stub init process, which does all of the reaping of the children and so on, signal forwarding and that kind of stuff, and then runs the actual binary that you want to run in there as pid2. And you can see what I mean essentially is, for us, this would be, somebody need to tell me if I'm doing very weird stuff, because this is going to be challenging. And then it's probably x2, I guess, and then bash. Don't worry about the warning, it's just a mount. So, but when you do a ps aux f right here, then you see, don't know if that works right now, but you basically see there is an init process, which is not really an init process, basically just a stub init whose only job is to forward signals and read signals, and then the second process that is running in there is actually the process that you want to run, and that's actually the proper way of running a process container. Being opinionated about this, of course. But so you see again, like actually this whole thing is much more in line with running an init system than it is running with a single process. Why are system containers sort of special? This is what I actually want to talk about, and I think I have sufficient time. But as I said before, in contrast to FreeBSD jails and Solaris zones, Linux kernel doesn't really care or give you a kind of container object or any virtualized entity in that way. It's rather actually for user space to build something that lets you create, run, and manage containers. For example, libelixy is one of those things. runC is one of those things. Systemd nspawn is one of those things. And this is what we usually refer to as a container runtime, I guess. And the interesting step, I think, is actually the creation part, because it means right now you're defining what a container is. And this is interesting in a lot of different aspects, and I'm just going to touch on a few of them. First of all, as I said, kernel doesn't really care what you do, what kind of process you run in there. It also implies that the kernel doesn't really care about giving you the right interfaces or even combining them in such a way that they let you run any kind of process that you're actually interested in there. So that's all on you, the runtime monkey. So you have to decide, these are the interfaces, this is what I need to do, and these kind of processes are able to run in there. But even from from the perspective of a process that wants to run inside of a container, it's also pretty interesting. Like my main example I always use is remember virtual machines. Imagine a virtual machine. It's basically, the idea always was, if I remember the research papers right, you basically create a one-to-one identical kind of, the way you run processes inside of a virtual machine and the way you run a process on the host, they shouldn't really differ at all. You shouldn't realize that there is any kind of difference. And if your virtual machine, for example, requires any given process to sort of behave differently inside of a virtual machine than it does on the host, then obviously your virtual machine implementation has likely done something wrong, right? I guess. So, and in some respect, containers have the same idea. What we usually want is to not have any kind of process need to do any sort of adaptation on how it is run inside of a container and on the host. But given the restrictions on how containers are implemented inside of the Linux kernel, this is actually not easily done, or at least we're very far away from actually getting to that point where like processes don't need to do a lot. And this especially touches on processes which are very powerful, right? And what is the most powerful process on your computer? Or basically the omnipotent process. It's PID1. So running pid1 inside of a container, like a whole proper new init system in there, is actually quite challenging for that respect, because if you're a process that makes a lot of assumptions about what it can do, how it can do it, what kind of abilities it has, and so on, then you're going to run into trouble if suddenly you find yourself in a situation where you are in a container, especially if you consider, for example, running in an unprivileged container, where sort of you have a mapping between the user ID inside of your container and the user ID outside of that container, meaning root inside of the container is not actually root on the host. That restricts a lot of the things actually a process can do. So what you essentially need to do as a process, I think, or as a container runtime, there are two ways to go from here if you're interested in running an init system. Either you adapt the container runtime in such a way that it makes it somehow possible to run a whole init system in there, which is fine. It won't necessarily work in all cases, given that the kernel also has additional kind of restrictions. Or, which is the second thing, you as a process make sort of compromises and, for example, say, okay, I'm running inside of a container, I'm ignoring this failure because obviously this will not work inside of a container. Again, it's a huge difference to a virtual machine. And this is for most processes, this sort of choice is clear. For an init system, not so much, which is totally fine. As I said, like, you're one of the most important processes that you actually have, that you have on your host. So it's totally fine if you leverage some of that power to get what you want. And actually, systemd has done a great job over the years at being more and more compliant with actually running inside of a container. The first, I think, few years when systemd also was relatively new and when liblxe was pretty new, this was all like new areas, I guess, for all of us, like sort of getting this to work and having to do with all of these horrible hacks and so on. I want to illustrate one more point where I think, like, for example, running an init system inside of a container is pretty difficult. For example, it comes along with kernel interfaces, and kernel interfaces not being designed for containers specifically. So, for example, C group management is one of my prime examples. So as an init system, using C group is pretty naturally, right? You can use it to, for example, track processes across double forks. You don't have to resort to all incredible, horrible ptrace hacks and so on. So they are pretty useful. And you might also decide, as an init system, will now become the C group manager, so to speak, of which systemd to some extent is, which is, again, totally fine. But now you run into a problem when you consider that it's not just the init system that assumes I'm managing C groups, or I want to manage C groups for a set of processes. I want to be able to move C groups around in the tree and so on, move processes around. You also have a container runtime, which basically assumes the same. Basically says, I want to manage my own containers, and I want to move them around, and I want to place them there, and so on. And then you move the init system inside of the container, and suddenly a lot of the assumptions about what the init system actually can do with C groups inside are broken, because it's inside of a container. They don't necessarily hold up anymore. There's a bunch of restrictions you can apply to C groups, especially inside of a container. So there's sort of a natural conflict going on, and that's actually quite challenging on a lot of levels. If you think, for example, you're an init system, you want to make use of the new features that a kernel brings, for example, user namespaces, you want to use pid namespaces yourself, you want to isolate processes, all of the interfaces that you basically are using as a container runtime, and this affects basically all container runtimes, to define what a container is from a user space perspective. Another program, not just an init system, might decide, I'm going to use this for myself because this is pretty useful. I'm a browser and I think user namespaces are really cool, and mount namespaces to isolate myself. And if you think about nesting all of these things inside of a container, then you can see that this is actually quite challenging. But so liblxe was actually designed with getting around all of these problems, and I think by now we can say with confidence that basically you'd be hard-pressed to actually realize that you are running inside of a container immediately. So libLXC is actually just a shared library. This is usually what people forget. It ships with a lot of tools, like low-level tools and so on, but in itself, it's just a C shared library that allows you to create and manage containers. And recently, we've been integrating libLXC with LXD, which is like basically a full-fledged daemon that allows you to manage containers as you would manage virtual machines. That at least that's the idea. So LXD exposes a REST API that can talk to a bunch of hosts over the network to spawn new containers and manage them. And but I don't want to go into too much detail. I don't want to make like this a big product statement or so on. It's just like really an interesting problem to have. I want to go into demo mode, and namely, I made the claim that we can basically run really a lot of weird stuff in there. And recently, when I was in Prague at the open source summit, I sort of thought, so what can you do to actually show like people you can do really weird stuff. And so who remembers CentOS 3? Which year did CentOS 3 come out? Like 2004. That's like kernel 2.6 something. And actually, I've gotten hold of one of those images, and believe it or not, let's see. Wait. Oh man. Oh come on. I should have just cloned. Sent one. Ah, look at this. Then make it send 2. Let's see if that works. So to show that it is actually a proper send3 container, we can look at the console log of send2. Is there a space? Log. There's a bunch of stuff that's obviously going to break, since this is like, as I said, like a really old kind of kernel. But you can see right here there is init system 2.85. This is sys5 init. This is a CentOS this is actually a CentOS container that's been booted. Like, this is really ancient stuff. And by the way, this is running on a 4.14 kernel with like some weird custom patches of mine applied. So that's actually quite fun. So you can also get a shell inside there, exec send2, and then do bash, and then you can see, right, there you have it, a send container. So and then by the way, I got cocky in Prague, and I thought, what about getting hold of Slackware 1.1? Which is like the first distribution in 1994, or came out in 1994. But the problem with this is, you'd think that ELF binaries are really old. They really are not. And I don't think you can run non-ELF binaries with or unless there is a special mode I don't know about. But I've gotten hold of a Woody container actually, which is like 1 year older. Crazy that works. Huh? Oh, Woody too. Right. Then you can see you have booted a Woody. You have booted a Woody container actually. You can actually by now you can actually even, I guess, TTY1. You can actually, if you wanted to, you could actually, I haven't set a password, so you would need to attach to it first, but you can actually also connect to a TTY. You can even by now have patches for this. You can actually attach to a TTY, so like you would do for a virtual machine or something. The interesting part is you can actually, I mean, you can detach from the console, but I'm not going to spend time on this. You obviously can run any new system you want right there. Like if you have, for example, right here, there is X1, right? That's a generic X1 bash, that's just a normal systemd container. So if you look in there, then you boot a full-fledged systemd container. And the interesting part is that this is actually a fully unprivileged container. And to show you the real craziness about this is docker run bash. I don't know if I have pulled it. Again. It's IT, right? Is it with dash dash? So it's a one dash right now? And then it's Ubuntu, right? And I guess it doesn't really matter, and then you do bash. Let's see if that works. I should have pulled it before because it was long. But it's basically, now you see that you're actually running inside of you're running Docker inside of a full-fledged like system container. The interesting part about this is if we look at less, and then we go down, and we look for, wait, Docker, where is it? And you see, you look at this right here, then you see it actually runs in a fully unprivileged container as well. Like this is, for example, your root inside of the container. So if you do IDU inside of the container, you will see your IDU ID 0, but actually outside on the host, like this is mapped to a fully unprivileged ID. So this is actually running systemd in a fully unprivileged container, which is like running Docker inside of it. So you really can do a lot of weird shit by now. And I'm sorry, you can do a lot of weird stuff by now. And the thing is that this is obviously, this is not just like a testimony to the power of liblxc and lexd. It's also like the kernel guys. I mean, I've just been running a Woody container on I don't know, on a 4.14 kernel. And actually, this is the fun part. This is a demo. I don't think I have time for this right here, right now. This is a demo I did in Prague because you can actually still update and install Debian Woody containers from 2003. So Debian is still letting you install Vim inside of there and all that kind of stuff, which is pretty impressive, actually. So making system containers in general work has been like an interesting challenge, and this is obviously a lot of guys who have done a lot of work. There is Eric Biederman, who is like one of the main guys who've implemented really like the core parts inside of the kernel. Search as well. Tycho has been involved in like a bunch of that stuff as well, especially getting Creo to work in liblxc and so on. So system containers are actually pretty fun and have pretty good use cases where you would usually just use a virtual machine. And I think with that, I'm going to finish before I'm just going to go on and give some more weird demos and so on. But if you have questions or want to yell at me, feel free. And thanks.
Okay, so we have about 10 minutes for questions. Okay.
Thanks for a nice talk. I have a question about unprivileged containers.
Yeah.
It turns out that this code actually runs as unprivileged user, but it runs the kernel code which previously was running as root. And it gives the ability to attacker to exploit the vulnerabilities in this code, which is not very clean or...
In the user namespace code itself, you mean?
I mean, when you run the unprivileged container, the actual kernel code,
Yeah.
which is previously was running for root, and it is old and buggy and so on, now runs as an unprivileged user. And now we have an ability to exploit.
So it basically boils down to the question, is the kernel implementation of user namespaces or in general clean enough to enable running containers securely? I guess that's what you're saying, right? I mean,
are there any solutions for that? I mean, what can we do to decrease the danger of that? I mean, to decrease the amount of
Well, there's a bunch
code
of...
in the kernel which we run.
So first of all, the kernel shouldn't have any bugs. That's the trivial answer, but that's also true for virtual machines or KVM. And if your KVM, like hypervisor implementation has a bug, then you're running into trouble as well. What you can do to mitigate the attack surfaces, I don't know, like there's a bunch of stuff. Most container runtimes, I guess, would enable you to use, for example, seccomp to block a bunch of syscalls. That would be dangerous. I mean, this is not so much a concern for, I guess, user namespace containers, although there are obviously also syscalls which you might want to block for unprivileged containers as well. There are LSMs, just as, for example, AppArmor and Linux. For example, we have a custom toy kernel that basically does, wait, what was it, Tycho? Linux on the host. And AppArmor inside of the container. So we're at the point where you can actually do LSM stacking, or people are actually working on this kind of stuff. So you can use a bunch of, so to speak, third-party kernel features to mitigate the attack surface. But you're right. I mean, in the end, it boils down to the kernel not having any bugs. Yes, of course, and especially in the user namespace code. I guess it would be my answer, unless I'm talking nonsense.
Okay, thank you. The next question. No one. Oh.
Related question. What, in your opinion, is the most interesting security attack surface for unprivileged containers? Is it, you know, mounts? Is it...
Oh, it's of course mounts.
Well, or is it... you know, these other system calls that nobody ever looks at, process read v, write v, something like that, or?
I guess the most interesting attack surface, first of all, is basically running anything inside. I think at least is running anything not non-trustworthy in privileged containers. So essentially not using user namespaces, because then you get a list of all of this, like all of the problematic stuff you essentially have, like a bunch of syscalls that you can perform, which you definitely shouldn't be able to perform, depending on the init system. Like, for example, I think with, what was it, the one for Ubuntu, Upstart, you could shut down the host and all that. So I think that's actually the biggest attack surface. For unprivileged containers, this becomes kind of interesting. I guess there's a bunch of, like what you pointed out in one of your talks in Prague is basically, if you do mount propagation the wrong way, then you're running into trouble as well. So there's basically a lot of implementation, I guess, implementation pitfalls you can run into.
Okay. Thank you. Next question.
Thank you for your talk. My question is, LXD is often compared to Docker, and in Docker we have a lot of instruments for building the images for the container runner. But I believe as far as LXD, the whole thing that it has is like you create a tar file with whole root of S and just kick it in. And for example, you should just run Woody and you probably have like prepared it. Are there any plans for like enchanted mechanisms just to say I want this and just packet me together?
What's going to happen at some point is definitely that this whole template system is going to be replaced, and I don't know if we will ever support something similar to, for example, Docker files. That's at least not on our roadmap. I've seen that Leonard, for example, you've written called a tool Macozy, which we were looking into actually, which was pretty promising actually. I don't know if we made a call on it, but for example, something like this would actually be pretty useful, so that you have an easy way to just, for example, generate a new image. I think one of the main problems we might have had, but I might remember this wrong, is that it's only for systemd-based distros so far, right? And so, for example, as I just demonstrated before, we for example, we do weird stuff like, I did not say the curse word again this time, like running Woody containers with like a sys5 init system or a send3 containers. We have sometimes customers that are like, oh, we want to run CentOS like 5 inside of a container. And we're like, sure. I mean, if you want to, but I don't know why. So that's basically the only blocker. But full-blown, like, basically you have a Docker file and then you, for example, say, I don't know, multi-stage builds and all that kind of stuff. That's sort of out of focus for us, I guess, at least at this point. If somebody wants to write something like that, like, I'm not opposed to it.
Thank you.
Thank you. More questions? Okay, so this means that question to you. What is the best one?
Oh God, yeah. Do we really have to do this? What is the?
It's up to you.
Now you're putting me on the spot. Now, I mean,
you just received scream.
they were all pretty fine. Can everyone get something?
That gentleman took already has a shot. So you have to select between two of them.
Okay. Tycho, you won't be mad because I know you well enough, so you're not getting anything. Yeah. But
okay, here already has.
Let's give something. What is your name? Sorry. Dmitry.
Okay. Thank you, and thank you very much for you.